Recording in progress.
So, comes on everyone. Let's start off. Last thing that we did was the junction law. We started with the junction law. This is what we did. Again, just to brief the steps. What is step one? You take any one point and treat it as a zero potential. Then find the potentials at the remaining nodes, and then choose the junction, and from there try to get the the charges. Clear? So let's see a question on this. Others do keep your cams on. Let's say this is C, this is 2C, this is C, and this is 3C, and this is C. Find C equivalent. Now, this is not a Wheatstone bridge. Let's make it 3C and C. This is an unbalanced Wheatstone bridge. So it's not a Wheatstone bridge. You can't use that thing. There is no series parallel. There is no symmetry, nothing. You have to go to Kirchhoff's law. Let's see how you do this thing. Give it a try. Take a minute or two, then I'll show you. Then we will see a little more variations on this. So how to take this thing? Step one, choose any point as 0. I will take the negative terminal as 0. Then this point will be V. So this is also 0. This is also V. This point will be, I don't know, it is not V, it is not 0. There is no wire. So this is X. This point, it is not V, it is not 0, it is not X. So it is something else, it is Y. So you have actually two variables, X and Y. You don't know both of them. That is the first thing, finding the potential at the nodes. Right. Next thing. So what about the charge flow? So let's say the charge here is Q1, this is Q2, and this is Q3. Here the charge is Q4, Q5, and Q6. It doesn't matter. These charges are exactly not important. You can say Q2 is equal to minus Q5. That is right. But we don't need them. You will see that. Now let's write the junction law at X. So you're assuming Q1 is coming from V to X. So this is the equation, right? Q1 plus Q2 plus Q3 is 0. Why? Because the total charge coming to a node has to be 0. Because charge conservation. All the charge can't enter, right? It will get stored then. It doesn't make sense. What is Q1? Capacitance into the potential difference, V minus X. So if you're taking charges coming from V to X, means you're assuming V is greater than X. Q2 is coming from Y to X, so that is C into Y minus X. Then 2C is coming from 0 to X. So you are assuming 0 is greater than X. So science will take care of it, don't worry. C will get cancelled, and then you'll end up with V minus X plus Y minus X minus 2X is equal to 0. This would be 4X minus Y is equal to V. This is your equation 1. Similarly, when you do the same thing for junction Y, Q4, Q5, and Q6 is 0. Q4 is coming from V to Y, so 3C into V minus Y. Q5 is coming from X to Y, so that's C into X minus Y. That's what I said. If you see Q2 and Q5 are reverse, you need not worry about that. And Q6 is coming from 0, so that is C into 0 minus Y is equal to 0. This is 3V minus 3Y plus X minus Y is equal to 0. This would be 4Y minus X is equal to 3V. This is your equation 2. So we have equation 1 and equation 2. From here we can get X and Y. Right? So if you solve this for X and Y, what do we get? Let's solve this for X and Y. So take Y from here. I'll just solve it. So Y will be 4X minus V. Take this and dump it here. That will be 4 into 4X minus V minus X is equal to 3V. That will be 16X minus this. That will be 15X. That will be minus 4V, 7V. X is equal to 7V by 4X minus Y is V. And did I mess up something here? Yeah, this was 5Y. Yeah, this is 5. 3Y and Y, na? 5 it is. Okay, Y is equal to 4X minus V. Take it and dump it here. That will be 20X minus 5V minus X is equal to 3V. X is equal to 8V by 19. You can solve this. So we'll get X is equal to 8V by 19. Similarly, Y will be, take it and substitute here. That will be 5V equal to 3V minus 8V. 19, 357, 57 minus 8, 49. Plus X, yeah, what calculate I'm doing? 50 and 65, 13. 13V by 19. Check. Yeah, numbers are not great. Then what? Question is still not over. You just found X and Y. So you found the voltages at those 2 points. Then what we do? Now, since you got X and Y, what is the charge flowing here? You said this is Q1 and this is Q4. That means from the battery, you're getting a charge of Q1 plus Q4. What is the definition of C equivalent? Charge coming from the capacitor, which is Q1 plus Q4 by V, isn't it? That's the definition of C equivalent, right? The charge given by the capacitor by voltage. And what is Q1 and Q4? Q1 is nothing but C into V minus X. Q4 is nothing but 3C into V minus Y by V. Substitute X there. The V will cancel anyway. You'll get C into 1 minus 8 by 19 plus 3 into 1 by 13 by 19. How much is this? This is 19 minus 8, 11 by 19 plus 19 minus 13 is 6. That is 18 by 19. That is 29C by 19. That's your C equivalent, everyone. Clear with this? This is how you handle them if you have an unbalanced Wheatstone bridge. Yeah, there are other techniques also. People say there is something called, star delta and all that. It would take the same amount of time. And that's a concept normally they teach you in second year in electrical. But if you are keen about that, you can do it. I'll send you a small theory on that. You can read it, but it is not there in our portion technically. But clear with this? This is, I took the toughest one, like, the brute force one. But if they want to ask you something like this, they will do something even better. But everyone understood the steps? So what they would ask would be something of this sort. Same question, if I give you like this. C, 2C. Sometimes they won't give the battery, they will simply say like this, 2C, C, and C. So the battery is between this. They'll say find C equivalent. So you have to assume an imaginary battery giving an imaginary charge Q. Now, before even starting the question, right? There is a more simpler way to do this. Matlab, something happens here. Look at that. There is a kind of a symmetry there. This is 2C and this is 2C. This is C and C. This is called a diagonal symmetry. So this will make your life easy by one step. It will reduce one step. So what is that? Listen carefully here. Let me explain you this and then I'll give you time to do it. So if you notice here, we have something called a diagonal symmetry. A diagonal symmetry is not really that powerful, but yeah, it will reduce the statements a bit. So what is diagonal symmetry? You can clearly see the left. I need to copy this, wait. If you see, these two are looking same and these two are looking same. Means what? Suppose if Q is coming from here, Q will come out from here. So if Q1 comes from here, can I say the same Q1 will be here? So this and this will have same charge. Agreed? Whatever happening from the front side, the same thing will be on the right side. Similarly, if this was Q2, then this is also Q2. Do you guys agree with this thing? Whatever happens here, the same thing will happen here. So these two capacitors will have same charge, and these two capacitors will have same charge. Sure? Now, this is the thing. Now, because they have same charge, see what happens. If this was 0, and if this was V, and if this was X, and this was Y, if you just look at this capacitor here, the Q1 capacitor, so Q1 will be C into V minus X, but Q1 is also C into Y minus 0. That means Y is nothing but V minus X. Basically, this is what is happening. Since the charge is same and the capacitor is same, the potential difference must be same. Since the charge is same and the capacitor is same, the potential difference must be same. Since this is already 0, potential difference must be Y minus X. Are you getting the logic there? So whenever you see a circuit like this, you can directly do something like this. You can say V 0. If you say this is X, what was the potential difference? The potential difference is V minus X. So same thing, what should be the potential difference? This also should be V minus X. So this point is directly V minus X. So you will eliminate one variable. It makes your life easy there. So this difference must be V minus X. Is this logic making sense? The logic is simple. Because the charge is same and capacitance is same, the potential difference must be same. Now, wait, I'll ask you one more. Now, you tell me how to do this thing. Because if they want to ask you, they'll make it more complex. Let's say you have a circuit like this. Maybe I'll give you resistors. Let's say this is B and this is A. All are R. Can you just name the potentials of the nodes? Let's say if this guy is V and this guy is 0, just tell me how will you name the alphabets. So totally how many nodes are there? 1, 2, 3, 4, 5, 6. You have to name all 6 of them. I can put capacitors also here. It's the same thing. Think for a minute. How will you name the potentials? Even though there are 6, you will get only 3 different potentials. Matlab, with only 3 variables, you can say there is a diagonal symmetry here. Whatever happens here, same thing happens here. Whatever happens here, same thing happens here. Whatever happens here, same thing happens here. So this is an extended diagonal symmetry. Okay, see. If I call this X, again, the logic is same. If this current was I1, you guys agree this is also I1. So this potential difference is V minus X. So this potential difference also must be V minus X. So this junction will be V minus X. Is that logic clear? Suppose if you take this point as Y, then this point will be V minus Y. If you take this point as Z, then this point will be V minus Z. Are you getting how to take the potential? So this potential difference is V minus X. This potential difference is V minus X. This potential difference is V minus Y. This potential difference is V minus Y. This potential difference is V minus Z. This potential difference is V minus Z. So the potential differences have to be same. That is the whole thing about diagonal symmetry. Please have a look at this. If you understood this, you understood diagonal symmetry. Is this clear? Any confusion on this? So now can you find the C equivalent then? So they will give you something like this. So instead of solving for X and Y, you have to solve only for X. One nodal analysis will give you the answer. That's the whole idea there. So how do you start? Let the charge be Q1, Q2, Q3. Find X. Then find the charge here Q4. Q1 plus Q4 by voltage is the C equivalent. That's how you play the game. They're not tough, but put some time, give it a good try, because exact same thing you will see again in current. So you're doing 2 chapters at the same time. So it's worth learning this. Okay, let's see. So this is how you start. Let this be V, let this be 0, let this be X, and let this be V minus X. Just doing this, you eliminated one variable. Let this charge be Q1, let this be Q2, and let this be Q3. So if you're writing for X, the junction law, Q1 plus Q2 plus Q3 is equal to 0. That would be C into V minus X plus 2C into 0 minus X plus C into V minus X minus X. C goes off, you get V minus X minus 2X plus V minus 2x is equal to 0. We get x is equal to 2V by 5. Perfect. And let this charge be Q4. So from here we are getting Q1 plus Q4. So Q1 is C into V minus x, which is 3CV by 5. Q4 is nothing but 2C into V minus x. That is 2CX. 4CV by 5. So C equivalent is nothing but total charge coming from the battery, which is Q1 plus Q4 by voltage, which is 7C by 5. Yeah, right, Amita. Clear with this? Now see, this was faster, right? Not too much work. These are the kind of questions you can expect. The previous one I asked you, that C, 2C, 3C, that was the worst thing that can happen. Nothing is balanced there, so literally you have to solve. But still can be done to equations, little lengthy. But this is a good one to ask. Can be done in 2 to 3 minutes because there is a diagonal symmetry. Any doubts on this? All clear with this? Great. So that's about the Kirchhoff's junction law. So you can use these junctions to figure it out. Now in Kirchhoff's law, there is another thing called Kirchhoff's loop law. What this thing simply says is the sum of the potential differences across the elements in a closed loop is zero. Means if you start at one point and if you go through different elements, and if you come back to the same point, it will be zero. I mean, that's kind of obvious, right? Because if you start at point A and if you come back to point A, then the potential difference is VA minus VA, which is supposed to be zero. It's like a conservative force. So if you start at one point and come back to the same point, it's a state function. The potential difference will be zero. But you can do this in a much better way. You can also use partial Kirchhoff's law. If you want to find potential difference between 2 points, I'll show you how this works. Is sum of potential difference across the elements in any path between the 2 points. Means if you want to go from A to B, you take any path. If you add all the potential differences in between them, the difference will be same in any path between the 2 points. Generally, if you want to find charges and all, I don't like this thing. But if you have multiple elements, later on we will see if you have a resistor, battery, capacitor, 3, 4 different things mixed up. This is a pretty good one. So this is the sign convention we need to follow. I'll show you the problems we did with this, how it will look. The sign convention is important. We use a very simple sign convention. When you go from higher to lower potential, the potential decreases. Listen to the sign convention. So if you have a battery, minus, plus, and V. So negative terminal and positive terminal. So if you go from left to right, you are going from negative to positive. So potential will increase, plus V. If you go from right to left, you're going from positive to negative, potential will drop. You have to write minus V. Is that convention clear? So whenever you cross a battery from negative to positive, it will give you potential extra plus V. If you go opposite to the battery, it will remove the potential V from you. Similarly, if you have a capacitor, plus Q and minus Q, if you go from positive to negative plate, potential will decrease, minus Q by C. If you go from negative to positive plate, potential will increase, plus Q by C. You can write down the sign convention. You will need this. Is the sign convention simple? If you go from negative to positive, it will increase. If you go from positive to negative, it will decrease. For a battery, it is plus V, minus V. For a capacitor, it is Q by C, minus Q by C. Copied? Now let's see how to use this to solve problems. Steps to solve. First thing, if there are multiple batteries, let's say there are 3, 4 batteries or 2 batteries, assume charge Q from any one battery, doesn't matter. Assume charge Q from any one battery. So you can choose any one battery as primary. Step 2, using junction law, distribute the charge with appropriate alphabets. Using junction law, distribute the charges at the nodes. Third, apply Kirchhoff's loop law such that all elements are covered. Means if there are 5 different elements, when you write equations, at least in one of the equation, the element should be there, like all elements are covered. That one element must come at least in one of the equation. I'll show you what it means. To find C equivalent, sometimes they will just give you a circuit and say find C equivalent. Assume a battery giving charge Q. And find Q by V. Just have a look at the steps. Let me show you an example. Let's take the example which we have already done. Which one? The same question. We already know the answer, so it works. Okay. Step 1, assume charge Q coming from the battery. I will assume 2Q is giving charge Q. So see, wherever the charge flows, I'll take that as a positive plate plus Q. Q will continue to flow. Let's say this is small q. So this will be small q. This side Q minus Q will split. So this is Q minus Q. And then Q will continue to flow. And then Q will come back. Is the charge distribution clear? So I'm assuming 2-volt battery is giving charge Q. That charge will split into small q and Q minus Q. And they will continue to flow and they'll come back to the battery. Now, take this as one loop and take this as one loop. Listen carefully to the sign convention. Not difficult. You just need to know the convention. Yeah, I'll take the left loop. You can start from anywhere. It doesn't matter. Let's say I'll start from here. If I start from here, I'm going to the left. Look at this thing. I'm going to the left from positive to negative plate. So minus Q by C. Then I'm going through the battery. Look at this thing. I'm going in the battery from positive to negative, minus V. Then I'm going like this, in the middle one. I'm going from negative to positive plate, plus Q minus Q by C, 2C. I came back to the same point, so the potential difference is zero. I'll do one thing. For convenience, let's call this point as A. So I'm starting at A, and I came back to A. So VA will be zero anyways. So this thing, simplify this. So V is equal to Q by 2C minus 3Q by 2C. This is your equation 1. Please have a look at that equation. You can ask me, sir, why did you take like this? Why can't you take that? You can take any direction, doesn't matter. The loop you took is random. You can choose any loop. The signs will take care of themselves. So if you take the right loop, again, I'll start from A. I'll go like this. I'm going down in this capacitor. See, how did I go? I'm going from positive to negative plate. That's what you have to check. And you can ask me, sir, how do you know that's a positive plate? I don't know. I assumed that is positive. So science will take care of it. Minus Q by 2C. Then I'm going through the battery. Battery, I'm going from negative to positive, plus 2V. Then I'm going again from positive to negative, minus Q by C is equal to 0. Again, if you simplify this, this would be 3Q by 2C minus Q by 2C. So we have two equations and two unknowns. So if I solve this, this would be Q minus Q. Q minus 3Q is 2CV. This is a 3Q minus small q is 4CV. Great. So take Q from here, which is 3Q minus 4CV. Substitute here. This will be Q minus 3 times 3Q minus 4CV. I hope I didn't mess up the calculations. That is Q minus 3Q, that is minus 8Q. This would be 12CV is equal to 2CV. It goes that side. 8Q is equal to 10CV. We get Q is equal to 5CV by 4. And small q will be, substitute there, 3Q, 15 by 4, 4CV by 4. Now, if you look at the chart distributions here, you said this is capital Q, which is 5CV by 4. You said this is small q, which is CV by 4. This was Q minus Q, which was 3CV by 2. Now, if you go back to that question which we did, we got the same answers, right? 5CV by 4, CV by 4, 3CV by 2. See? Are you clear how we did? Now, the reason why I don't like that method is just try to see. When you solved the junction law, what did you do? You just wrote one equation, see, and you got an answer. One equation only you wrote. You wrote only one junction law and you got an answer for X and you got everything. The problem here is you have to write two equations and there is a good chance you will mess up one minus sign somewhere and the whole thing will go for a toss. Small q is negative. Did I get small q negative? Yeah, negative I am sorry. Yeah, this was right. All clear with the steps. So both the methods will work. Both the methods are nice, right? But the only thing is this is a little lengthy. And the reason it is lengthy, I'll tell you why. In nodal analysis, what did you do? You said let one potential be zero, isn't it? When you said one potential is zero, you eliminated a variable. That's the reason you'll always get one equation less in junction law compared to a loop law. That if you see the mathematical reason, that is the reason. By choosing one potential as zero, you actually made the variables one less. So you'll get one equation less. But I'll show you this also, where this is really powerful. This is also not something which you can go down. So what we will do, let's do one more question. Now you guys try. The important thing is I want you to know how to write the equation. So I'll give you a question. I'll show you the chart distribution. You just tell me the equations. So we will not solve it. If you got the equation, then you're right. the most important thing is the sign convention. So this is V, C, 2C. Let's write this guy only, 3C and C. Okay, so we have to find the charges on the capacitor. Now, before you writing the equations, let me give the distribution, because if you write the distributions, all will get different equations. So let the battery give charge Q. So listen to this carefully. So Q is coming from here. Let this side go Q1. So this capacitor will get Q1. So I'm marking the positive plates with red color. Then this guy will be Q minus Q1. This is the positive plate. Then let this guy go Q2. So this charge will be Q minus Q1 minus Q2. Then this charge will be Q1 plus Q2. Then these both will combine and Q will come out. Is the charge distribution clear? So every time you get a node, you have to keep on splitting the charges or adding the charges. Now what I want you to do, write equation in this loop, write equation in this loop, and write an equation going through the battery and going through the upper two capacitors and coming back to the battery. These are the three equations. Because see, when you wrote this loop and this loop, you never wrote an equation through a battery. That is the meaning of that. You should make sure all the elements should come at least once. Now, can you guys write the equations? Just the equations. This loop, and a loop through the battery, the upper two capacitors, and back. Right, I'll give you a minute and then I'll show you. Then you can verify whether you got the same equations as me. So if your equations are right, you're done, you'll get the answer. Mm, Done with the equations? Okay, let's see. I'm writing the left loop, so check your equations. You can start anywhere, it doesn't matter. So only thing the terms will be left or right, they'll shift a bit. Oh, Param typed it also. So let's see. I'll start from this corner here. I'm going in that direction. See, it is simple. Are you going from positive to negative or negative to positive? That's what you have to ask. Are you going through a battery or you're going through a capacitor? So I'm going through a capacitor. I'm going from positive to negative, minus Q1 by C. Then I'm going to the middle capacitor. Look at here. I'm going from negative to positive plate, plus Q2 by C. This is C actually. Please see if you messed up a minus sign. And if you're confused, ask me. Again, I'm going here from negative to positive plate. So plus Q minus Q1 by 3C. That's your equation 1. You came back to the same point, so 0. If your starting point is different, you will get the same equation, but terms will be little, jumbled up. I'll start from here. I'm going to the right side. I'm going from positive to negative, minus Q1 plus Q2 by 2C. Then I'm going through this guy. This is the positive plate. So plus Q minus Q1 minus Q2 by C. Then I'm going from positive to negative. Minus Q2 by C is equal to 0. I'm taking the big loop. That will be V minus Q1 by C minus Q1 plus Q2 by C. And then you came back to the battery. You could have actually gone like this in the middle, and you could have taken any path. It doesn't matter. Please check your equations. Just have a look at this. Any doubts on the equations? Anyone didn't get a sign? If you got these equations, you understood Kirchhoff loop law. Any doubts on this? Great. Now let's see a question where junction law, will make you go mad. So both the techniques are important. Technically, you're talking Kirchhoff's junction law, loop law, right? They talk about the same thing. In the formula Q is equal to CV, the junction law talks about V, the Kirchhoff's loops law talk about Q. So kind of you're talking about the same thing. Where are you? Capacitors. This is the circuit. Okay, so all capacitors are C is equal to 20 microfarad, right? And those are the two batteries there. Find the charge on this C, the one which is marked clearly. How do you do this thing? These are called maze circuits. Maze. So think for a minute, then I'll show you. Okay, I'll tell you one thing. When you get these kind of questions, right? The thing is, if you can find a path where, look at the Kirchhoff's loop law, what it says. When you go through a battery, it is V or plus V or minus V, right? When you go through a capacitor, it is plus or minus Q. That means as long as you go through only batteries, it really doesn't matter what is the charge flowing in the battery. So these things, right? Let's name them. These are called maze circuits. So when you have a name, it'll be easy for you to remember. So what I want you to do, find a path or find a loop where C is the only capacitor and you can pass through any number of batteries. And number of batteries don't matter. And we can pass through any number of batteries. So listen to this. I'll show you this. I'll ask you one more like this. We can pass through any number of batteries. See. So let's start from here. So let's say on this, the charge is Q, N minus Q. Okay. I'll start from here. Now be careful. Huh? Don't touch a second capacitor because the moment you go through a capacitor, I don't know what is the charge here. And it will be some Q2 or Q3 or Q4. So I don't know how to solve that. So don't touch a capacitor. So keep moving. I'll go like this. There is no capacitor. No capacitor. No capacitor. So as long as you don't touch a capacitor, there is no problem. There, I passed through a battery. Did you notice something? I came back to the same point without touching a second capacitor. Now, if you write a Kirchhoff loop law, इसमें क्या आएगा Kirchhoff loop law? 20 minus Q by C. You came back to the battery. So Q is equal to 20C. C is nothing but 20 microfarad, so 400 microcoulombs. Easy. Are you sure what I did? That's it. So if you can find a path where you're going only through the battery and that one capacitor, you don't touch a second capacitor. So you must have done this thing in school, right? Newspaper में आता था. There is a mouse there. You have to draw a path for the mouse to reach the cheese. It's a maze. All clear with this? I'll show you one more like this. So you just have to find the path, okay? We will not solve that question. We'll solve that later on if you want. This will come in current. So there. So forget about the question. Don't worry about the question, okay? We just need to find this current. So can you find a path where this resistor is the only resistor and remaining all are batteries? If you touch one more resistor, you'll get an extra variable. We don't want to do that. This is also a maze. So you have to pass through that resistor, the one in the red, and you can pass through any number of batteries. Figure out. I'll give you a minute. Once you got this, I'll show you. You can check whether you got the same path. You can just see it on the screen and figure out. Don't draw it. You have to pass through this red resistor and find a loop. You have to come back to the same point without touching a second resistor. Found it? There. So your maze skills will come into picture here. So see, let's go like this, go like this, go like this, go like this. There. You could have actually gone like this also. That also would have worked. So if you take this path, you will not pass through a second resistor. You'll only go through batteries. So actually you can solve. This is plus V, this is plus V, this is plus V, this is minus V because you're going opposite to the battery. This is plus V and this is minus V. So the total voltage will be V plus V plus V minus V plus V minus V minus I into R is equal to 0. So we get 2V is equal to I1R. In the question, it is given voltage is 10 and R is 4. So we get I1 is equal to 5 amperes. So we will see this thing. This I'll show you this question again in current. But everyone got the path? Yeah. So you can play like that. So these are called maze circuits. All clear with this? The next thing. Now every time you won't get a battery. Sometimes you'll get scenarios like this. Let's say this is another important bunch of models. Let's say we have connecting two capacitors with a switch. Let's say this is 2C and this is C. So this capacitor has charge plus Q, minus Q. And this guy is empty. There is no charge on this capacitor. Now, when you close the switch, charge will transfer between them. Find the final charges and the heat produced when the switch is closed. This is one important bunch of things. Give it a try. I'll show you one and then we will do more. Hmm. Right, Param. Right, Samyak. Okay, let's see. So how do you solve these kind of questions? Listen to the process. The process is important. If you got the process, then you can handle any variations of this. So when you close the switch, this was 2C and this was C. This is how we start. Assume charge Q has flown from the capacitor. So assume charge Q is going from any one capacitor. Step one. So since there is no battery, right, the capacitor will play the role of a battery. Not a perfect battery, but it does. So assume charge Q from a capacitor. You can choose any guy, right? Step two, then do the charge distribution. This is a simple question because there are only two capacitors. It is easy to handle. Next question I'll show you. What if you have three capacitors or if you have a battery also included? So find new charge distribution and apply Kirchhoff's law. Okay. So assume Q charge will go from the battery. So how much charge will be here? Q minus Q. Remember, this is the positive plate. So this Q will come and hit this plate. So how much charge you'll get? Q. The charge Q will continue to flow and the charge Q will come back. So remember, if you say charge Q is coming, it has to go and come back, right? And then apply a Kirchhoff's loop law in this thing. So you can start from anywhere. I'll start from here. Minus Q by 2C. Then you're going from negative to positive plate plus Q minus Q by C is equal to 0. How do you know which is the positive plate? We are assuming it. Since the charge is coming from here, I said this is the positive plate. Since the charge will come and deposit here, so I'll take that as a positive plate. If it is wrong, the signs will take care of themselves. You solve this, you will end up Q is equal to 2Q by 3. Clear with this? So that means what are the final charges? So that means the upper capacitor gave 2Q by 3 charge. So you are left with Q by 3 minus Q by 3, 2Q by 3 and minus 2Q by 3. This is how you do charge distribution. What is the heat produced? Initial energy plus work done by batteries. There are no batteries minus U final. So initial energy, there's only one capacitor, Q square by 2C. Battery is 0. U final will be Q by 3 whole square by 2C plus 2Q by 3 whole square by 2C. 2 times 2C. Yeah, you solve that, you'll get the heat produced. Are the steps clear, everyone? Like I said, this is a easier version. You could have done without all this story, but the process is important. Clear how we handle this? Let's see the next one. Let's say we have three capacitors with a switch. This is C, this is 2C, and this is C. Let's say this thing has a charge of 3CV minus 3CV. This thing has a charge of minus CV plus CV, and this guy is empty. Find the charges when the switch is closed. I just want to ask you something. Are these two capacitors in series? For two capacitors to be in series, what should be same? They should have same charge. They're not in series. So be careful. Just because you're side by side doesn't mean you're in series. Get this. How do you start? Assume a charge Q is coming from any one capacitor. Let that charge Q keep on going round and come back. Get the charge distribution, apply the Kirchhoff's law. They're nothing. These two capacitors are not in series, not in parallel. They're nothing. For parallel, you should have same potential difference. For series, you should have same thing. They should be across same nodes. So here, that doesn't make any sense. So okay, let's see. So step one, assume charge Q is coming from any one battery. Okay. So I will say this guy is giving charge Q. It doesn't matter. You can choose any one. So if that guy is giving charge Q, then how much charge will be left here? You initially had 3 CV. Now you'll have minus Q. Remember, I'll only mark this thing positive plates. I'll put the positive plates as red, remaining I'll keep it as blue. So this Q is flowing. See, this is how you should think. This Q is flowing. It hits this plate. How much charge was there on that plate initially? Nothing. So how much will you have now? Q. The charge Q will continue to flow forward. Technically speaking, it is inducing charge, isn't it? But it gives you an illusion it is flowing. So this Q is flowing. It will hit this plate. Initially, how much was there on that plate? Plus CV. Now how much you'll have? Q plus CV. And the charge Q will continue to flow and will come back to the capacitor. Is this thing clear? If you do like this, right, I'll tell you'll not have any confusion. It will be like clear. Oh, aisa karna hai har baar. So having a process is important. In the exam, when you're under that pressure, right? If you have a technique where you're not confident or it gives you answers sometimes or you do a lot of mistakes, it will put your pressure. When you can follow one process, even in that pressure, that's the important thing. So apply Kirchhoff's loop law. Start from anywhere. I'll start from here. I am going from positive to negative plate, minus Q by C. How do I know that is positive? I don't know. The science will take care of itself, so we will know. So you can assume anything is positive. Again, I'm going from positive, Q plus CV by 2C. Then I'm going from negative to positive plate. So 3CV minus Q by C equal to 0. C will go off, minus Q by 2, minus CV by 2, plus 3CV minus Q is equal to 0. This will be 2Q, 5Q by 2. This is 5CV by 2. Q is equal to CV. Remember, what this is a charge going from the capacitor, okay? This is not the final answer. I hope my calculations are right. So what are the final answers? Equations are right now. 3 minus 1 is 5 by 2. Yeah, look right. So this guy will have a charge of 3 CV minus CV, 2 CV, minus 2 CV. This guy will have CV minus CV. This guy will have 2 CV minus 2 CV. Yeah. Is the answer clear, everyone? Understood how we did this? Any doubts on this? All clear with this? Let's see one more. Looks like got the same thing. So I think we are right. PCB. Any doubts on these equations? Or did I mess up any calculations? The answer is so good, I'm doubting myself. So, okay. Let's see one more variation of this. Two capacitors, C, 2C. This time we also have a battery with a switch. Let's say this thing has a charge of minus 3 CV plus 3 CV. This is empty. Now when you close the switch, find the final charges and the heat produced. See, if there is a battery, assume Q is coming from the battery. If there is no battery, assume Q is coming from a capacitor. Battery is the primary driver. If there is no battery, then a capacitor will take the role of a battery. So keep the process simple. If you have a battery, assume Q is coming from a battery, distribute the charges, apply Kirchhoff's loop law. If there are no batteries, then choose any one capacitor, let it play the role of a battery. As Q is coming from the capacitor, distribute the charge, apply Kirchhoff's law. That's it. The story is always the same. Let's give it a try. Okay, let's see. The switch is closed. Remove the charges here. We'll start like this. Let the battery give charge Q. You can say, sir, capacitor is giving charge Q. Fine, you can do that also. You can say capacitor is giving charge Q. You can still play that game that way. You'll still get the answer. It doesn't matter. Only thing, your Q and my Q will be different. So if the Q is flowing here, simple thing. Initially, how much was there already? Initially, you had minus 3 CV. And now you are giving extra Q. That is how you should say. So now you will become Q minus 3 CV. I will assume this is positive. How do I know? I don't know. So let it be positive. Science will take care of it. This Q won't stop here. This Q will continue to go. How much was there initially on this? 0. So this guy will get Q. That will be minus Q. Q will continue to flow and Q will come back to the battery. So that is the main theme. Anytime you say Q is coming out, it has to go round and come back. Clear with that? Then apply Kirchhoff's loop law. I'll start from the battery. I'm going in the battery from negative to positive, plus V. I'm going to the capacitor, Q minus 3 CV by C. I'm going to the capacitor minus Q by 2C is equal to 0. This would be V CV minus Q. Let's write that up. V minus Q by C plus 3V minus Q by 2C. This is 4V is equal to 3Q by 2C. So Q is equal to 8CV by 3. Interesting. So that is the charge which has gone through the battery. Right? So what are the charges on the capacitor? So the final charges will look like this. Q minus 3 CV. That is actually minus. So this guy will have minus CV by 3. and this is plus CV by 3. That plate is actually negative. We thought it was positive. The science will take care of itself. And then this guy is 8 CV by 3. This is minus 8 CV by 3. Yeah, that's your final charges. All clear with this? Or did I mess up somewhere? Any doubts on the equations? All got this stuff. Be careful here. C and 2C are not in series. They don't have same charge. Just because you're side by side doesn't mean you're in series. Don't do that mistake. You can clearly see they don't have same charge distribution. If initially they were empty, then you could have said it. Okay, so this thing gave 8 CV by 3. We still have to find the heat produced. So this is a good question. If they ask you heat produced, it will be good more than one choice question. What is the work done by battery? Work done by the battery is the charge flowing through the battery into voltage of the battery. That will be 8 CV square by 3. What is the initial energy? Only that capacitor had energy. How much was that? 3 CV. So 3 CV whole square by 2C. What is U final? CV by 3 whole square by 2C. That is one capacitor energy. 8 CV by 3 whole square. This is the second capacitor energy. What is the heat produced? Initial energy plus work done by battery minus U final energy. Substitute that, you'll get your answer. So in this case, what happened? Initially, the capacitor had some energy. When you connected the battery gave you some more energy, and the whole thing got, dissipated and did all that thing, and yeah, you got a lot of heat. Okay, we have got 16 by 9 CV square. So on capacitor C, why it will not be 3 CV minus Q? Because initially ये plate में कितना charge था, Vanchika? Minus 3 CV ना? So for minus 3 CV, you are giving plus Q. तो कितना charge होना चाहिए? Q minus 3 CV. Got it? If this had been plus 3 CV, then yeah, what you're saying was right. So it is always like that. The battery gave you Q, but you already had something initially. So that plus the new one. Clear? Hmm. Any doubts on this? This is a pretty good question. These models are really good ones. The capacitor is already having initial charge and you're putting a battery and you're doing all these things. These questions have come a lot in mains, meaning more than this battery thing, na? And these questions with the three capacitors one, these are very common questions in mains. So if as long as you remember the process, you'll be able to handle them easily. Clear with this? Take a break, come back by 9:45. We'll continue with this. We'll do one more model like this. But any doubt so far? These are some pretty good ones. Anyone confused with distribution or anything? Please ask.
So why can't we take the other plate for writing the equation? Equation?
Meaning, which plate you want to take?
Like in
इसको
हाँ
ले सकते हो. मतलब see, the thing is, पहले decide which is your positive plate. You are saying you want to take this as a positive plate? ठीक है, no problem. So अगर वो positive plate लिया तो ये positive plate तो इसमें charge कितना होगा? 3 CV minus Q.
it will be nice.
Now see, when you're writing the equation, when you go here, you're going from which plate to which plate? Negative to positive. तो ये प्लस होना चाहिए यहाँ पे
Oh, okay.
और अंदर प्लस और माइनस हो जाएगा तो इनडायरेक्टली से माइनस से मल्टीप्लाई किया ना तूने. So that's what I'm saying. It doesn't matter. You take whichever as a positive plate, the sign will take care of itself.
Okay.
ठीक है? Yeah. चलो, come back by 45. Okay, let's ahead. This would be a paragraph type. So this is a battery 2V, this is V, this is C, and this is also C. Here we have a switch. So this was A and this was B. You can flip the switch between A and B. So you can connect the switch to A or B. So initially switch is at A. Then find the charge distribution and the heat produced when the switch is flipped to B. The second part. Now, if the switch is flipped back, so you kept it at B, then you took it back to A again. So just because of flipping the switch, in that process, how much heat you get? If the switch is flipped back to A, find the heat produced. Let's get these two. Let's see how you do this thing. Others, do keep your cams on. Okay, let's see the first one. Now see, you just have to be careful with the circuit. You just keep drawing it. So initially the switch is connected to A, right? So this is how the circuit will look. What about this battery in the middle? It is useless. It is just hanging in air. It's not connected to anyone. So you can remove that. So this is C, this is C. So this capacitor 2 volt will not work. This is V. We can clearly see both the capacitors are in series. Why? Because they're initially empty. So this will have charge CV by 2 minus CV by 2. CV by 2 minus CV by 2. So this is the initial situation. Okay. Now what you did, you flipped the switch to the point B. This was A and this was B. Now when you flip the switch to B, your circuit becomes like this. This is C, this is C, this is V, and that is 2V. Now, because of this, something will happen, and we don't know how much charge will flow. So let Q charge flow from the battery. Now, if Q is flowing here, you already have how much here? You have minus CV by 2 here. So this charge will become Q minus CV by 2. Q will go into this battery and Q will come back to this. So this Q is flowing round, round, round and comes back here. What about this capacitor? This capacitor got disconnected. So this will still have the same charge that will be unaffected. So keep that in mind. If you take a capacitor and if you keep one side in hanging in air, nothing happens. Do whatever you want, that charge cannot go anywhere. Because if you want to change this charge, then this CV by 2 also should change, but where will it go? It is stuck in space. Is this distribution clear, everyone? Please ask me if you're confused with this part of the step. The moment you close the switch, some charge will go from the battery. We don't know how much, we don't know which way it will go. So I will assume 2V is giving an extra charge Q. Apply Kirchhoff's law in this loop. That will be 2V minus Q minus CV by 2 by C minus V, because you're going opposite to the battery, you came back to the same point. You do this, you'll get CV V, so you'll get Q is equal to 3CV by 2. So this much charge goes from the battery. So what is work done by batteries? Now you have to be careful here. The 2V battery is giving you energy, 2V, but the V battery is absorbing, so it is Q into V. So that sign convention is important. If the charge comes out of the battery, it is giving you. If the charge goes into the battery, it is absorbing. So this is Q into V. So this is 3CV square by 2. There. And what are the final distributions? These are the final charges. So Q minus CV by 2. So this guy will become CV. This will become minus CV. This will remain CV by 2. And this will be minus CV by 2. These are the final charges, everyone. Have a look at this. So this battery gives small q, that is 3 CV by 2. So 3 CV by 2 minus CV by 2 becomes CV. What is the heat produced? You can find the initial energies. That is this much. So remember, this is your initial condition. You want to find the heat when you close the switch. Plus work done by batteries minus U final. You can substitute that, you'll get an answer. Is this process clear, everyone? Now, second part of the question. Now you took the switch and kept it back at A. Now what is the heat produced? Try. I'll give you a minute or two. Now, if you took this switch and kept it back at A, something happens. Again, charges will redistribute. You have to find the final charges and find the heat produced. So the final state of part A becomes the initial state for part B. Hmm. Okay, let's see. Now when I flip it back, What were the initial charges? This was CV. This was minus CV. Minus CV by 2, and this was CV by 2. These were the initial charges. Now you're saying I'll flip back the switch. Now, let me ask you this question. Do you think these two are in series? We don't know. Are you sure both have same charges? We don't know. So let this give charge Q. How much is there initially already? You already have minus CV. So how much will be there now? Q minus CV. Let the Q charge continue to flow. How much is there here? CV by 2. So this guy will become Q plus CV by 2. This 2-volt battery will do nothing. This Q will continue to flow. The Q will continue to flow. The Q will come back. I hope this story you're getting. Every time Q will go, it will keep on, distributing and will come back. Apply the Kirchhoff's loop law. So if I apply the Kirchhoff's loop law here, I'm going from the battery. V minus of Q minus CV by C minus Q plus CB by 2 by C equal to 0. Solve this. CV minus Q plus CV minus Q minus CB by 2. We get 2Q is equal to 3CB by 2. We get Q is equal to 3CB by 4. This much charge flows through that battery. So what is work done by the battery? Now we can figure out that. So there's only one battery doing work now. The 2-volt battery is useless. So work done by the battery is Q into V. So this is 3CV square by 4. What are the final charges? Most common mistake what people do now, people think these two are in series. They're not in series anymore because they don't have same charge. What are the charges now? Q minus CV, this was 3CV by 4. So this is minus CV by 4 and this is plus CV by 4. Q plus CV by 2. So this is 5CV by 4 and minus 5CV by 4. They're definitely not in parallel. Look at the distributions. That's what makes this question really good. This will be a pretty good advanced paragraph question. Are you clear with the steps? So every time you keep flipping the switch, the charge will keep on messing up. So the heat produced will be U initial plus work done by battery minus U final, and then you're done. Any doubts on this? Okay with this? So let's see. That is the one more thing. Let's see. One more little easier one. This is more of a standard model. Sometimes, right, they won't give you charges. They'll ask you like this. They will say there are two capacitors. C1. This is plus and this is minus. Charge to potential V1. This is C2 plus minus. This is charge to potential V2. Then they will say, in case 1, both the things are connected in same polarity. Means you connected the plus plate to the plus plate and negative plate to the negative plate. Same polarity. Other possibility, you connected them in reverse polarity. So the plus plate of C1 is connected to negative plate of C2. This is the reverse polarity. Now when you do this, the charges will again redistribute. Find the new potential difference across the capacitors. Two different questions, everyone. This is a pretty good standard means level question. Let's see how you do this. So instead of giving charges, now they're giving voltages and stuff. So what we do, the process is pretty straightforward. We do the same thing, but I want you to remember the result for this. So how do we do this thing? I'll show you the one first case. So this was C1, this was C2. You connected the same polarity. So let's say Q charge goes from anywhere. So let Q charge flow from here. So this guy ka charge will become C1 V1 minus Q. This guy ka charge will become C2 V2 plus Q. Apply Kirchhoff's law. Minus C2 V2 plus Q by C2 plus C1 V1 minus Q by C1 is equal to 0. And then you can simplify from here. You will get this is minus V2 plus Q by C2 plus V1 minus Q by C1. And from here you'll get Q ka value, which is C1 C2 by C1 plus C2 V1 minus V2. And then if you go and substitute back in that, potential difference will be, it looks big and long, but if you do this, you'll get a pretty good answer. So potential difference, you can take any one of them, C1 V1 minus Q by C1. And if you substitute the value here, you end up with C1 V1 plus C2 V2 by C1 plus C2. There is a logical way of also why this will happen. Because when you connect them end of the day, they will have the same potential difference. So from there, you can say the potential difference is there. So you can remember the answer. So for this guy, the answer would be the new potential we knew will be C1 V1 plus C2 V2. That is your new charge by C1 plus C2. For this guy, the answer will be, you're just keeping them in reverse. So C1 V1 minus C2 V2 by C1 plus C2. We are assuming C1 V1 is greater. Clear with this? So that's an easy way to remember the answer. So the results are more important, saves you time in exam like means or bits. But this is how you do. End of the day, the process is the same. Any doubts on this? There. This is one important thing in capacitors, that you're connecting two different capacitors with different potentials and different charges and all that stuff. Any doubts so far? Next thing, the last part in capacitors is dielectric slabs. Now this will give you some feeling of conduction and heat transfer. We will do a bit of a theory today. Next class we will wrap it up. Not a difficult stuff. So we saw in order to increase the capacitance A epsilon by D, increasing area was a bad idea. Decreasing distance was creating dielectric breakdown. So the only thing that is left is a medium. So if area of the plates was A, and if the space between them is vacuum, and the distance is D between them, the capacitance is given as C vacuum was A epsilon by D. What if you fill this entire space in the middle with some kind of a medium? So let's say you fill up this whole space with a dielectric slab. Okay. Dielectric slabs are insulators. They are not conductors, so charge cannot pass through them. So they have very less free electrons. The K is nothing but dielectric constant, which is nothing but epsilon R, which we studied in Coulomb's law. If you guys remember, this is also called as relative permittivity. So it is the same thing, relative permittivity, that epsilon R, which we studied in Coulomb's law. For some reason, they changed the symbol to K here. So yeah, we will stick to it. There's this charges in a medium there. This is the thing where you got introduced, dielectric constant or relative permittivity. The same thing, that epsilon R is only all called as K here. I know there are so many K's, spring constant, that, this, everything. But yeah, so this epsilon R, which is epsilon medium by epsilon naught, this is only the K. So they're the same thing. So now what happens to this thing? So C of this capacitor, when you keep the medium, will become A epsilon medium by D, but epsilon medium is simply K into epsilon naught by D. This becomes K times C vacuum. So whenever you fill the whole space with a slab, the thing actually increases. The capacitance increases by K times. For example, generally they use zinc sulfide. ZNS, zinc sulfide, this epsilon R or K ka value is around 8.3 or something. Means by coating with a zinc sulfide inside, you can increase the capacitance by 8 times. And it also has multiple advantages. So think of like this, you have two bread ka pieces and you put a thin layer of jam. The thinner the layer, the better, because you can decrease the distance now, and you can also increase the medium ka epsilon R. So it's like a thin coating here. So this is a coating of zinc sulfide. Yeah, now they use better materials. This is one of the example, that's it. So we can use materials with higher and higher dielectric constant. So, and not only this thing, because of a thin coating, right, the two plates will not stick together. It will provide some mechanical strength. And if you take conductors, for conductors, epsilon becomes infinity. For conductors, K tends to infinity. Great. So capacitance is increasing. So what is exactly happening inside the dielectric slab? Like, that's the thing we need to figure out. Now look at this. So when you take these two parallel plates, which have some charges plus Q and minus Q, now you're going and putting a slab in between them. Let's say there's a small gap there. So what actually happens, right? Remember I told you this in dielectric thing. Because you don't have enough free electrons, what will happen? The electrons will get pulled towards the left side and you'll get a positive charge here. You'll get dipoles. In case of a conductor, the electrons are completely pulled from the nucleus and they go and get deposited on the surface. But in an insulator, the electrons can't come out, but they will try to move away a little. So in this process, you get dipoles. So dipoles are formed inside. If you had kept a conductor, the electrons would have been completely removed from the nucleus and they would have gone and got deposited on the surface. Consider a dielectric slab between the two parallel plates. So, in the dielectric slab, the concentration of electrons is negligible. That is the reason they are insulators. Concentration of free electrons is negligible. Hope you remember what is the free electrons? These are the electrons which can move freely across the lattice. And this electric field, what happens? The external electric field creates dipoles. So it will still pull the electrons, but they can't come out. Creates dipoles. So basically, you'll get a dipole moment inside by moving electrons and nucleus apart. So this is what would happen. So this is a nucleus, and this was the electron. So this will get pulled here, EE, and this will get pulled here, EE. So this guy is going in some kind of a distorted orbit. Clear with this? Now, because of this, what will happen? You will start getting an induced charge on the dielectric slab also. So on these two parallel plates, if you take the charges, this is how the distribution will look. So let's say this charge is sigma. So this plus sigma will create an opposite charge on the plate, but it will not be equal to minus sigma. It will be minus sigma induced. Why? Because you don't have enough free electrons. And this side you have minus sigma. This minus will create an opposite charge. But because you don't have enough free electrons, you will get some partial charges. And these dipoles are so close, right? We can assume this plus and this minus will neutralize, this plus and this minus will neutralize. So it gives you a feeling there are charges only on the surface. So you get plus sigma and sigma I. So you get induced charges on the surface. Due to dipoles, there will be an induced charge. In case of a conductor, it used to be equal and opposite. On the surface of the dielectric. So now what happens? These plates are creating a field sigma by epsilon. These induced charges are fighting back. They're also creating a field sigma induced by epsilon, but they're not strong enough. So field due to the plate is sigma by epsilon. The field due to that induced charges on the dielectric is sigma induced by epsilon. And we know from Coulomb's law, whenever you put charges inside a medium, the field becomes 1 by k times, the force becomes 1 by k times. Field inside a medium becomes 1 by k times. So that means, see, this is the scenario. So in that slab which you have taken, right? If outside the field was E, then the field inside would be E by k. And once you come out again, field becomes E. So the inside the field will decrease because of these dipoles. The dipoles will decrease the field. So E inside is nothing but the field due to the plate The reason you're decreasing is because of that induced charges, E induced. So E inside is sigma by K epsilon, it becomes K times. E plate is sigma by epsilon, and this guy is minus sigma induced by epsilon. And this gives you a very good result. We have seen something like this in Coulomb's law. I also taught you this, the force due to the induced charges. We get sigma induced is equal to sigma into 1 minus 1 by K. This is the induced charges. So whenever you keep a dielectric in front of a plate, you won't get equal and opposite charge. You'll get these induced charges. I'll show you an example. For a conductor, K is infinity. Then sigma induced will be equal to sigma. So that's the reason you'll get equal and opposite. Example C. For example, if you take a plate and if you take a dielectric, let's say this is a conductor, and let's say this is not a conductor, this is a dielectric. And let's say K is equal to 3. Now, if someone asks you this question, this is charge Q and this is neutral, find the charges induced on the surface. I know we can, K is actually epsilon R, but everywhere in the book you'll find K only. So then you'll get confused. We saw this in Gauss law, distribution of charges in parallel plates. So here the formula will be a little different. So the distribution would be whatever is the charge induced here, that will be opposite there. So what is the charge on the outside? Total by 2. That is still valid. So this is Q by 2. This is Q by 2. So here, how much will you induce? This would be small q. This will be minus q because it's neutral. And how much is small q? Small q is the charge q by 2 into 1 minus 1 by k. K is 3. So 1 by 3, 2 by 3, q by 3. Okay. That is the charges, everyone. Sorry, this is minus, this is plus. Understood? How the charge distribution works? That formula is still valid. Outside is how much? Total by 2. That's only for a conductor. For a dielectric, you will induce this much charge. There, that's your whole derivation, like what happens exactly inside. Is this clear, everyone? Let me give you one more example. You tell me what's the distribution for this. Let's say you have a conductor, we have a conductor, and we have a dielectric slab. And let's say here K is equal to 2. Let's say this thing has a charge 2q and this thing has a minus q charge. This is neutral. Find the charge distribution. So for conductors, that formula is same. Equal and opposite plates will have, the facing plates will have equal and opposite charge. The dielectric is a mess. Done. Let's see the distributions. So how much will be outside? Total by 2. Only for a conductor. Don't do it for a dielectric. What is the total? So here will be q total by 2. That is q by 2. If this is q by 2, this is 3q by 2. This is 3q by 2, this is minus 3q by 2. If this is minus 3q by 2, this is plus q by 2 because total has to be minus q. Then this has to be minus q by 2, 1 minus 1 by k. K is again 2, so this is minus q by 4, and this is plus q by 4. Got the distribution, everyone? This is how you handle if you have a dielectric slab instead of a conductor. These are some pretty good ones. They're not too tough, but these are not generic questions. Any doubts on this? So this is what happens here, and because of this dielectric slab, we can also just take the picture from here. We define something called a polarization. Polarization is defined as the dipole moment of the induced charges per unit volume. That's the definition of polarization. What is the dipole moment? Sigma induced into distance by volume is A into, sorry, Q induced into distance. dt will cancel. This will be Q induced by area, which is nothing but sigma I. So induced charges is the polarization. So sigma induced is sigma into 1 minus 1 by k. That's it. That is just a quantity. There's nothing much on that. All clear with this? So that's something what happens when you put a dielectric slab. Your capacitance increases, you put induced charges. Because of all that stuff, right? Things will change a lot. Great. So simple thing. When you put a capacitor, capacitance increases. That is the main thing. And remaining all this stuff is what happens with the dielectric actually inside. The questions would be pretty straightforward. They'll actually give you the, the feeling of the heat transfer. Let me show you a question, you'll understand. Let's say we have two parallel plates. The upper half is filled with a dielectric K. The lower half is filled with 2K. In heat transfer, we call this thing thermal resistance, thermal conductivity. Here we're calling it dielectric constant. The distance is d between them. Area is A by 2, area A by 2. Find the C equivalent. Let's get this. So the upper half is filled with K and the lower half is filled with 2K. Find the equivalent capacitance. Exact same questions we have seen in heat transfer. Their K was thermal conductivity. This was K. This was 2K. This was 3K. So this area was A by 2. This area was A by 2. This distance was d by 2 and this distance was d by 2. I hope you remember this also. This was that special case. Find C equivalent. Yeah, 3 by 2. In case you're confused about this thing, right? This is where you have to go and you can revise heat transfer. This was the question, if you say. Page 21. Exact same question. We can treat them like, see, even there, I wrote it like capacitors only. They look like capacitors. There's no difference, except those are resistances. Page 21, heat transfer. Yeah, 3 by 2. Yeah, right out here. Right over here. Get the second one also. I forgot. Last class I gave you a homework question. Did you guys try? Oh, integral E1 dot E2 dv wala. That is one thing I gave you. So let's do that after this. 10 by 7. So how do we do this thing? This is straightforward. You can treat them like two capacitors. So divide this into two parts. One capacitor and one capacitor. And both are in parallel. So इसका area क्या होगा? A by 2. Distance is this. D. This area is A by 2. So you can treat this thing as this is filled with K. So this capacitance will be K. Area is A by 2 epsilon by D. This is 2K. So this will be 2K. Area is A by 2 epsilon by D. Since both are in parallel, you just add them up. C equivalent is equal to 3 by 2 K A epsilon by D. Easy? Straightforward. What about this guy? Hope you remember this. You cannot take 2K and 3K in parallel. That is because this interface and this interface are not identical. They have different potentials. Here, 2K and 3K are not in parallel. Unfortunately, even in JEE mains, I think 2021 or 2022, they did ask and they took them as parallel. So yeah, if it comes in mains, I think maybe you can check which answer matches. But advanced math, if you do that, you'll definitely get a wrong answer. We can always argue in advance, but mains, I don't know why they do such nonsense. So then what we do, then the only way to handle this is we have to split this into four parts. Where each capacitor ka area is A by 2, distance is D by 2. A by 2, D by 2. A by 2, D by 2. So all areas become half and all distances become half. So this guy ka capacitance, this will be K, this will be K. So this would be K into A epsilon by D. This will be K into A epsilon by D. A by 2, D by 2, they will cancel. This is 2K into A epsilon by D. This is 3K into A epsilon by D. You can clearly see the upper two are in series, the bottom two are in series, and they're in parallel. How much are you guys getting for this? 17 by 12, AFK, A epsilon by D. Yeah, Samyak, I think. You can verify this. That's your C equivalent. Clear? That you can handle series parallel. No, that's what I said. This thing has a very similarities to heat transfer. So that's a bit about that. Next class, when we catch up, we will continue with that. And let's see that homework question one. Anyone got an answer for this? So listen to this thing. This is right. Is a we have to interpret the mathematical equation. That's the interesting part about it. Okay. So see. So we have Q1 and Q2, right? Let's say E bar, which is E1 bar plus E2 bar. This is the field due to the both the charges at any point in the space. Field due to Q1 and Q2 at any point. Great. That means if you take the system, the total energy of the system, can I write this thing as half epsilon E square, that is the energy density, into dV for the overall space? I'll just say all space. You guys agree with that? If I take the field due to these two charges at everywhere, and if I integrate half epsilon E square dV everywhere, that should be the total energy of the system. Now, if I try to expand this, half epsilon is constant. This will be integral E1 bar plus E2 bar ka square dV. And if you expand this, you will see this will be half epsilon E1 square dV plus half epsilon E2 square dV plus 2 will cancel epsilon. This is where you get it. E1 bar dot E2 bar dV. Can you see the term? E1 bar, E2 bar comes to there. Now try to understand the meaning of this. This is the total energy. But if you notice carefully, this term is nothing but the field only due to Q1. So if E1 is the field only due to Q1, then isn't this term the self energy of Q1, which is K Q1 square by 2R1? Is that making sense? If you take only the shell Q1, what is the self energy of the shell? K Q1 square by 2R1. Where is this energy stored? Half epsilon E square throughout the space, isn't it? Similarly, if you look at the second term, this is the field only due to the second shell. This is the self energy of Q1, Q2. So this term, if you actually can integrate, this would come out to be KQ2 square by 2R2. Then what's left? The interactional energy. The total energy of a system is self energy plus interactional energy. So this term must be the interactional energy. So this is the interaction between both the shells. And since both the shells are very far, we can treat them as point charges. This is K, Q1, Q2 by L. Is that logic making sense? So the total energy of the system is your own self energy, and the interaction between them, isn't it? There are only three parts for the energy. And we can clearly see the first part is giving self energy, second part is giving self energy. Then from there we can argue, then this part must give you the interaction energy and there's no other option. Are you clear with this? And then we will say, so epsilon integral E1 bar dot E2 bar dV was K Q1 Q2 by L. You wanted E1 bar dot E2 bar dV. So that is how you get from the mathematical term. You see like what does this even mean? Since charges are very far, we can treat them as point charges. If you keep the charges pretty close, then it gets messed up. Then we can't actually figure it out. We know it is interaction energy, but we don't know the value. That's what makes this question good. We will see the same thing again later on in magnetism. But is the logic making sense? All clear with this? That's a good one there. Okay, so that's the main thing there. So we have done almost 29 questions. So please make sure to go to the capacitors. We're almost done. I think next class, first half of the class, we will finish off capacitors. And then we'll start off with current introduction. So we'll finish off current electricity and then we'll go for ray optics. So we'll take a small break there and then we'll come back to magnetism. So that way. Okay, with that, we'll wrap up for the day. So any doubts, anything else, please stay back and ask. And do remember, there's a test online. So make sure to give. I'll see you guys again next Tuesday. So yeah, take care, stay safe. So any doubts, do ask me.